डायरेक्ट कर देते 13 पार्टिसिपेंट अच्छे बर्तमान लिंक कर देखिए डायरेक्ट जॉइन कर
गुड मॉर्निंग सर ईमेल Good morning, sir. Please turn on the video.
Hello, good morning. Am I audible?
Yes, sir.
Yeah, Ullasji is
Yes.
there? Ullasji?
Yes, yes. Am I audible?
Yeah, fine.
Okay.
So shall we start the session?
Yes, yes.
Yeah, on behalf of Regional Science Center, I welcome all participating teachers, and same time I would like to convey my sincere thanks to TIFR team. That's Dr. Surendra Kulkarni and Ullas Vaidya from TIFR Science Popularization and Public Outreach team. And I'd like to convey my sincere thanks to Professor Arnav Bhattacharya, Center Director, Home.
Your mic is muted. Your mic is muted, sir. Not listening anybody.
Okay. Am I audible?
Yes, sir.
Yes, sir.
Yeah, I welcome all participants on behalf of Regional Science City. Very warm welcome to all of you. Once again, I welcome Dr. Surendra Kulkarni and Ullas Vaidya from the TIFR team. It is privilege for us to having Dr. Surendra Kulkarni and Ullas Vaidya in today's sessions. I would like to convey my sincere thanks to Dr. Surendra Kulkarni and Ullas Vaidya from TIFR Science Popularization and Public Outreach team. And same time, my sincere thanks goes to Professor Arnav Bhattacharya. It is a privilege to have the TIFR team in this science demonstration festival. Right now, I would like to request Professor Ullas, Dr. Ullas Vaidya to take, this is right now, this forum is yours. And please go ahead. I hope that teachers will be hugely motivated and will be inspired through their, demonstration will be performed by the Dr. Ullas and Surendra Kulkarni. Thank you.
Okay. So, could you spotlight me so that it will become full screen? Excuse me, sir. I think you need to spotlight me. Yes, yes. Okay. So thank you very much for the kind introduction. And at the very onset, a happy Science Day to everybody. And I would like to say that I am not a doctor. I am only a science communicator at TIFR. And what we do here is we try to show experiments that bring to fore what is already there in the books, so that rather than the thing being a dry abstract subject, it becomes something that everybody experiences almost every day. Okay, so that's what we do. So the purpose of our outreach is that. Okay, so now day before yesterday we had a wonderful talk from an Australian speaker. Unfortunately I don't recall his name. So normally what we always say, this is a very simple thing. What I have done here is a protractor, and to which I have attached a small mirror. Is it visible? Yeah, I think so. So normally what we say is that light ray, the angle of incidence is same as angle of reflection. Is that correct?
Yes.
Yeah, but for a student, it is very difficult to understand what exactly is meant by that. So if we take a simple protractor, which is available in all geometrical boxes, we just fix a small mirror, and then we see that I think this is not that great. Okay. Just a minute. Okay, do you see that? So we always say that the angle of incidence is same as angle of reflection. Okay, this is a very tiny tool, which I think can be easily made in a classroom, and we can demonstrate it to students. I think this is clear. Shall I go ahead? Okay. So much so for the reflection. So now when a light is incidence onto anything, some part will be reflected and some part will be refracted. So now let's look at a small demonstration into what is known as a refraction of light. So I just have a glass of water. Now let's see what happens. I have this arrow drawn on a piece of paper. Nothing happens, right? Now let's see this. Can everybody see a change in the reversal of the arrow direction? So why this happens? That's the question. Anybody? Anybody in the audience can explain this? That when I'm holding it upright, right, there is no change in the direction reversal. But when I hold it horizontally, what I see is this. Basically, arrow is pointing to my right now on the paper. But when we look through the small jar filled with water, the arrow direction is reversed. Can anybody tell me why this happens? What is the science behind this? I think if we make it conversational, it will perhaps be more fruitful. Okay, all right. So I think for audience here, reflection of light is pretty obvious. So, all right. So now let's do a tiny experiment. So what I have here is basically candles. Okay, candles of various lengths. And we all know that when we lit a candle and we deprive it of oxygen, what should happen to the flame? If we deprive it of oxygen, will it go off, or will it start blazing? That's the question we can ask to the students. So let's lit up the candles. And now let's try to cover all the candles one by one. Okay. Now, what I expect everyone here to do is to kind of get a rough estimate of time. Think of a rough estimate of time after which the flame went off. Okay. Can everybody see that all the flames are lit? 3 flames are lit. Okay. So I'm going to cover flame one by one. First, let me cover the tallest candle. And let us say that 1, 2, 3, well, at the most 4 seconds. And then the candle went off. And now let's take an intermediate length. 1, 2, 3, 4, 5, 6 roughly. Now let's take one more, the smallest candle. Now I say that all the beakers are of the same size, 250 milliliter standard beakers. And let's see how long does this last. 1, 2, 3, 4, 5. Okay, slightly around 5 or 6 seconds or so. So can anybody tell me why are these times different? Why did it take a different time for every candle to go off? What's the science?
So is it when the bigger the candle, the more oxygen it needs?
To start with, basically we are using a standard same 250 milliliter beaker. So oxygen is, if we say is roughly 20% in the air, then oxygen is same in all the beakers. It's not different. Normally, what we study in books is like the flame goes off when the oxygen gets over. Right? Is that correct or not really correct?
Yes, correct, sir.
Okay, so now the question is, why is it that it took different times? Okay, so this question is for you to ponder about, and perhaps you can pose it to your students also. Now let's change this experiment slightly, and instead of using 3 beakers and 3 different size candles, I am basically using candles of 3 different sizes. Okay, and we'll use just a single beaker and see what happens. So our hypothesis is the candle goes off when the oxygen gets over. Now let's see how far that hypothesis is really true. Okay, so I'm sorry for a slightly bad camera here, but I think it's okay. Everybody can see it now, right? Now, all that I'm going to do is just cover this up, and now let's see what happens. Oops. The times are different, right? Is that correct? Okay. I think, is everybody convinced about why we are doing this experiment? Actually, in any science teaching or learning or demonstration, the purpose of the experiment should be stated very clearly. Okay, so the purpose of this experiment is to test our hypothesis, wherein we started with an assumption that the flame will go off when the oxygen is fully consumed. Right? Now, in our first experiment, what we did was we took candles of 3 different lengths and covered them with a beaker, and we saw that, well, the times were not exactly the same. And now we have done this a corollary of that experiment, and we see that the tallest candle goes off first, the intermediate length goes off later, and the smallest candle goes off in the end. So now why is it so? If the oxygen was really over when the first candle went off, the other 2 candles also should have gone off, but they were lit. So any guess as to why is it so? any wide guess is fine. If we make it interactive, it will perhaps be easy to convey what exactly I am trying to convey over here. Should I repeat the experiment?
Is it, sir, that is it so that oxygen level is higher in lower level? It is not like that also. Carbon dioxide is more in the lower level.
Okay. Okay. So now what I will do is I'll can I give you some time to ponder about it and we'll come back to this experiment. Meanwhile, we'll go over to something else. Is that okay with everybody, or shall we complete this and go over to the next? All right. I think we shall complete this and go over to the next. So what is happening is, see, we are starting with a standard 250 milliliter beaker. So roughly we can say that the total oxygen in this is 50 milliliter, 20% of the volume. Okay. So now when the candles are burning, we know that the gas that comes out, the burnt carbon dioxide gas, is actually hot. And the hot gas will go up. So this hot gas going up will actually push the. Is everybody agreeing to this? That hot gas will go up and the cold gas will come down?
Yes, sir.
Okay.
Yes, sir.
So this hot gas, essentially carbon dioxide, it starts to collect at the closed end of the beaker, the upper end of the beaker, not the open end, the closed end. And the tallest candle is closest to the closed end. So it so happens that there is oxygen in the beaker, but it's not close enough for the flame to sustain. For the flame to sustain, it will always require a continuous feed of the oxygen. So we also notice that when the flame goes off, it kind of starts to go from yellowish to slightly dark. We see that more and more soot to start getting collected. This is basically because of incomplete burning, because of unavailability of the oxygen. So it's not that the oxygen in the beaker is over, it is just that oxygen is not available near the flame physically to sustain the flame. Okay, so this is what happens, and subsequently since the cold gas gets pushed down, the oxygen gets pushed down with it. So the first candle, the tallest candle goes off first, then the intermediate level, and then the smallest one. Okay, now having said this, we also have a question as to, well, when the smallest candle goes off, can I at least at that time say that the oxygen was fully consumed? Will that statement be true? So what is expected is basically when we are teaching basically combustion.
It will be not fully consumed. I think it will be not consumed fully.
Yes, yes, it will not be consumed fully. Again, the same reason stands that there is oxygen, but it is far away from the flame and the flame cannot sustain. So now this brings us to a very interesting theoretical problem, which you can perhaps try to solve in a classroom. Is that after, let us say that you have burnt 1 unit mass of wax in a similar experiment, and then how much oxygen is really left in the beaker? Can we estimate in terms of number of moles of the gas? So it is possible, it is very much possible, and I leave it for you to work on it. Okay, so now the next part of the experiment is this, is we'll come to it a bit later. So now let's worry about what is very common is, let's say, pressure. Now let's do a simple experiment. Like I guess in Orissa you have a big Makar Sankranti and kite festival in Jan. Unfortunately, I can't speak Oriya, but let's do a simple experiment which kind of helps in explaining some kite physics. Okay, so I have just taken a strip of paper, a small strip of paper, and I'm going to blow it. So please see carefully how I hold it and where am I blowing it. Okay, I'm holding it below my lower lip and I'm blowing straight. Okay, so initially you see that the far end of the paper, due to gravity, it is actually down, it's towards the floor, and when I blow over it, it actually moves against the gravity. If you have a piece of paper at your hands, you can do it yourself and test this. Can somebody repeat this experiment and confirm what I see is really the physics or really some science behind it, and it's not just some artifact. This is the fluttering, right? So can anybody say what is this? Why did this happen, or why do the kites fly, or for that matter, what is it that keeps the
pressure decreases with increase in air's wind speed?
Yes. So this is basically essentially what we can say is the Bernoulli effect. What I am doing is, by blowing, I am reducing the pressure over the upper surface of the paper, but elsewhere it's all higher atmospheric pressure, so that ends up pushing the paper up. So when we fly the kite, we what is it that we do? We basically it's basically just a piece of membrane and then we tie thread to it, and the thread is tied in such a way that if suppose I am flying the kite from here, the kite is never tilted like this. The kite is always tilted like this, like the back of my hand, like this, right? Still it's like this. The kite will always fly something like this at an angle. If I am flying the kite from here, it will be like this. Why can't the kite be like this? Any reason? Why is it that whenever we fly a kite, why is it always treated like this and never like this, or never straight for that matter? The reason comes from the fact that we cannot separate the lift and the drag. Okay, this again comes from the Bernoulli's principle, and we cannot, physics wise, it is impossible to separate the lift and drag. That's the reason. Okay, so now we have done this. Now let's do something about diffusion. We all breathe, right? Our body absorbs oxygen in the air through a process called as diffusion. We all know it. So now what I'm going to do is, in this glass of water, I'll take a water at room temperature, and in this I'm going to pour hot water. Okay, okay. And all that I'm going to do now is I'm going to drop some color into it, which in this case is just potassium permanganate. I'll take the camera closer to the glasses so that it can be viewed clearly. Right. So these are our glasses. This is warm water and this is cold water. I just dropped some potassium permanganate into it. Let's see this. Do you see patterns forming? And now let's put it in this. Do you see the difference? Okay. So this small experiments, which can be done without much of an equipment, can perhaps come very handy when you are introducing concepts to the students. Now, why we see that in cold water, the diffusion is relatively slower than in the warm water. Everybody agrees that in the warm water, basically, it took place at a much higher speed over the slow water.
Sir, is it because of convention?
Yes. So this is this is why we show these experiments which bring the contrast to fore, so that the concept is conveyed more effectively. Okay. So now Okay, we have covered diffusion. Now, what next? When we discuss about water, there is always a phenomena called as surface tension. Now, I want to ask a question. Is surface tension a force? Is it a force or it's not a force?
For unit length.
Okay. So contrary to what many may say, surface tension is not a force. Okay. Surface tension is a phenomena brought by the molecular interactions. Okay, and it's not a force. So now here we can clearly see that I have filled the water in the cup and it is above the upper layer of the upper edge of the curve, right? Okay. So now, is it possible for me to float, let us say, a paper pin? Can I float a paper pin on this? Because or will it sink? What will happen? I wish to put a paper pin in this, and I want it to float. So do you think surface tension is strong enough to?
Section wise.
Am I audible?
Yes, sir. Yes.
Okay. So let's do an experiment. So what I have done here is a very simple thing. I'll just take the pin. This is a normal paper pin. Okay. And I'm holding it in a tissue paper so that when I drop it, it basically drops reasonably flat and doesn't tear the surface. Okay. So now let's see. Let's see what happens. So what we see is, well, in this experiment, it did not work. It went to the floor. Now let's repeat our experiment. Okay. Now we can always say that, well, right now paper is a membrane, the tissue paper membrane is still there and it is perhaps holding the pin. But that is not so. In some time we'll see that the paper will get fully wet and it will sink to the bottom of the glass, but the clip pin will continue to float. Now, why is it that this pin always go to the edge of the glass? Anybody? Why does this pin always go to the edge of the glass? Why can I never hold it at the center of the glass? Any guess? Okay, so part of the reason is curvature of the surface.
Sir, let me know that a pin will.
Is the curvature of the water surface that drives it to the edge. Okay. See this, right? Here. Okay. So, okay. So far all good. Any questions about surface tension? Why is it that does all fluid have the same surface tension? That's the question. Do all the fluids have the same surface tension? And why is it different? We say that water has a very high surface tension when we compare with other fluids. Why is it so? Okay, I'll leave that question for you to think about, and I think the answer is pretty straightforward. If you think for it for about a few minutes, you should get to it. Okay. So now we have covered some part of light by way of looking at refraction. We covered some part of the heat or let's say Boyle's law by looking at this our candles experiment. We looked at surface tension. Now I think it's time to make some sound. Simplest experiment, simplest instrument, right? Shall we do flute or will not do flute? All right, I think we'll skip flute and we'll go over to magnetism. We are all surrounded by electromagnetism. All our modern life is possible simply because of electromagnetism. So now the starting point we can say is that, well, there is a magnet. What is a magnet? Magnet, we can say that, well, a magnet is a phenomena or a reality of nature in which certain materials are attracted to the magnet. So that we call such magnets as such materials as magnetic, ferromagnetic materials. Then certain materials are actually repelled by the magnet. We know that this is a magnet, they are basically magnets. There is a north pole, there is a south pole. If I try to bring north pole to north pole, it will basically repel, or south pole to south pole. Now, but if I bring close, unlike poles, they will like attract each other. Now, let us say that, what does this do? Now, what happens when I try to bring a magnet close to a current carrying wire? Or, okay, I think, is this experiment visible? Yes. Can everybody see the copper wire? It's not very visible. Okay, now I think everybody can see the copper wire. This is a copper wire and this is a magnet. What I'm going to do is I'm going to pass a current through this copper wire and see what happens. If I don't have a magnet, suppose I remove the magnet and pass the current through the wire, nothing happens, right? The wire doesn't get deflected. Now let's see that I'll put a magnet close to it, and now for the convenience I'll show the battery this side. So let's say that this is the positive pole of the battery, the small one is the positive pole, and this is the negative pole of the battery, and I'm going to pass the current. So what we'll do is that once we'll pass the current from this side to this side, and then we'll reverse the current direction and see what happens to the wire, whether it gets deflected, and if it does get deflected, then in which direction does it get deflected. Shall we do this experiment? Okay, let's see. Okay, so it got deflected towards me. Can everybody see it? Right? And then let's reverse the direction of the current. I'm just simply going to reverse the direction in which I'm connecting the wires. And then it comes in the opposite side. Can anybody tell me why is it so? What exactly happened?
Due to magnetic effect of current?
Yes. So what happens is that when the current is passing through the wire, it generates its own magnetic field which goes around it, right? And when that field interacts with the field due to magnet, we see that the wire will get deflected depending on the direction of the current. If the current is in one way, then the also if I reverse this, then depending on the, then if earlier if I was passing the current from left to right, and then if the wire was going this way, now I can expect that for the same thing the wire will go this way, right? So now where do we see this? This is a very simple experiment which indicates that the electricity and magnetism are not two independent phenomena, they are intertwined. Okay, so we see the impact of this effect will basically be seen.
Sir, in all solenoids. In all solenoids.
Solenoids, yes.
In all electromagnets in our day-to-day life use. We
Yes.
find such
yes.
effects coming into play.
Yes, correct. So basically the purpose of this demonstration is just that when we tell students that what happens when the current is passed through a wire, we say it, right? We solve problems on board, but if we show this demonstration, it will perhaps make it easier for the students to understand it. Okay, so now let's look at something called as diamagnetism. So what is diamagnetism? A diamagnetism is something which basically when I bring a magnet close to it, it will basically be repelled by the field. So now fruit, can a fruit be magnetic? I think yes. Let's see. Let's see if grapes are magnetic. So what I have done is I have some grapes here. Basically, okay. So in this experiment, what is done is let me get some background. Okay, the two grapes are basically fixed to sides of a stick and it is hanging. Now, why is it hanging? It is simply because this diamagnetism is very weak in this, and if I keep the grape on the floor or on some surface, the friction will not allow the diamagnetism to show the impact. Okay, so now what I'm doing is I have very strong magnet. Mind you, these are extremely strong magnets, total field more than 5 kilo-oersted. Now I'm trying to bring it close to the grape. Let's see what happens. Now in this position, the grape is more or less steady, right? Now if I bring magnet close to the grapes, see, I'm not touching it. Do you see grapes going away? Okay. Now let's put it in the other side. Let's see. If I bring it close, okay. Let's repeat it. Okay. So why we do this 2-3 times is again simply because an experiment needs to be done few times before reaching the conclusion, or our conclusion may not really be correct. So in this case, what happened was actually the grapefruit has a very high water content, and water is actually diamagnetic in nature. Okay, so this is what happened. The diamagnetic nature of water played up, and then that basically drove the grape away from the magnet. Now, if I do this experiment on the floor, let us say that I take a grape. So I have taken the same grape out and I keep it on my table. Okay. And now again, I try to bring the same magnets close to it. And nothing happens. I'm not able to focus it. Just give me a minute. Okay, I think this should be good. Okay, now see, there is a very tiny gap when the magnet was suspended onto with the support of the string. This much gap, and now I am actually able to push the grape with the magnet. Okay, now why is it so? Now this is so simply because of the friction. The force, the diamagnetism, the push that this magnetic field is giving to the grape is insufficient to overcome the friction. And that is why we see that when this experiment is done on the floor, the grapefruit doesn't move at all. Okay, so this is why I mean, the purpose of doing this experiment is also to maybe I think some of you had already were aware of this experiment. Is that correct? Okay, I assume at least few of you were aware of this experiment. So the friction basically would not have allowed this effect to be seen prominently, or not at all for that matter. Why prominently? Not at all. So this is about diamagnetism in grapes. And now we come to the last part of it. Now what I do is basically I take a copper pipe, then I have a plastic pipe, and I'm going to drop a magnet through it. Let us see what happens. Okay, firstly through a plastic pipe. Let's see how long does it take for it to fall. Okay, say, and it came down instantaneously, almost instantaneously. Okay. Now let us push it through the copper pipe and see what happens. One, two, three, four. It took much longer. Can anybody tell me why are the times different? See, the bore of the pipe is very large compared to the diameter of the magnet. So there is no friction. I'm able to drop it freely. So any idea why are the times so different when I drop the magnet through a copper pipe and when I drop the pipe through a PVC or a plastic tubing? Any idea why is it like this? Okay, so I think I will perhaps tell you the thing. What is happening is plastic is an electrical insulator, whereas copper is not. So when I'm dropping the magnet through the copper pipe, it is actually setting up what is known as eddy currents. Okay, so these eddy currents essentially go around. Since my magnet is like this, the field is like this. It can be either north or south, that doesn't matter in this. So it sets up these circulating currents, set up a magnetic field, their own magnetic field, what we saw essentially in our earlier experiment as well. But the direction of this field is opposite to what this magnet has. So if suppose this is north and this is south, then the current direction in this will be south here and north here. So this will essentially be repelling, and that is why it slows down the magnet. So now the question is, if this is the condition, then can we have an equilibrium state wherein the magnet doesn't come down at all? Why can't the magnet remain forever suspended in the center of this tube? Can anybody tell me why? Okay, I think I'll leave you with that. I'll leave this problem for you to work on, and let's go on to, before we end the session, let's go back to our flame physics. So is the flame hollow? If I say a candle flame, is a candle flame hollow or is it a solid filled thing? Any idea?
Sir, can you repeat the question?
A candle flame, is it hollow by nature? Is it hollow or is it solid? When we look at it from outside, when I look at it, it looks like solid, right?
It's hollow.
Yes. But is it really a solid or is it hollow from inside?
Hollow from inside.
The hollow.
It's hollow, right? Yeah. So can we demonstrate hollow nature of the flame? Do you think it is possible? And if yes, then how? And why is it hollow? Why can't a flame be solid? A candle flame?
Lack of supply of oxygen towards inside.
Yes, correct. So what is happening is entire oxygen is basically being used up from the side. So there is not really enough oxygen for the combustible fuel at the center. So easy way to demonstrate is I just take a tea strainer and I hold it over the flame. And now I don't know how to show it, but let me try and show it on camera. This is just a T strainer what I'm using.
Sir, not visible.
Yeah, it's not actually. I'm trying to see it on my monitor. It's not visible. Just a minute. I need to orient the camera properly. Yeah, you see it now? It's not very clearly visible, but I think you can make out.
Yes, sir.
Okay. Now I think it's very clearly visible. Okay. So this also brings us to another interesting issue, is that when we say that the candle flame is hollow, what is the temporal variation? What is the temperature variation if we across the cross section of the flame? Can that be measured? Do you think it can be measured? It can be another wonderful science experiment for you and for your students to repeat it. But yes, it is possible to do it, and it will give you very interesting insights into how the combustion happens and why is it the way it is. Also, you can perhaps ask your students to estimate the amount of energy obtained by burning per unit fuel of it. That's it. So that will also make them think about composition of material, and other physics of it. Okay. And now, lastly, let us say this. Okay, does it work? Okay. So a matchstick. If I take a matchstick, is a matchstick magnetic? I have a matchstick. Okay. Is it magnetic? Perhaps no. Okay. But when I take a burnt head of a match, this is again going to be tricky to show. Okay. So what I have is a burnt head of a match. Okay. And I bring a magnet close to it. Let's see what. Let's see what happens. It gets attracted. Okay. Yeah, just once. Give me a minute. I'm not able to focus the camera on it. Okay, let's see. Okay, so this is a head of a burnt matchstick, and I have a magnet, and I'm only going to bring it close. Gets attracted. Okay, so why is it like this? Any idea? Why is it that non-burnt matchstick head is not attracted to a magnet, but a burnt one is? Any idea why is it like this? Okay, so that is last kind of thing from me for the time being for you to think about, and I think I'll take questions. Already time, yeah. Can I take questions now?
Sir?
Yes. Yes, go ahead.
So what is the experiment used to find out the temperature inside the flame?
Okay, so there are actually several routes. One route is to actually put a small temperature sensor, and like we did the strainer experiment, you use a strainer and run a temperature sensor from outside to inside and see per unit displacement of the sensor, what was the temperature variation. Other experiment, you will require a mobile phone with a camera, in which it will give you a colors. It will give you the color of the flame. You can focus the camera and detect wavelength of the light at a particular position. Okay, so if suppose this is your flame, this is the flame, and then you focus the camera on it. At this point you detect the color, at this point you detect the color, at this point you detect the color. This way you detect it, and then this wavelength you can correlate with the temperature. Okay, so this way you can find out the length versus temperature profile of the candle flame. Is it clear?
Yes, sir. Thank you, sir.
Okay. Any other question? Okay, so can I take a few moments to tell you about my institute? Hello? Sir, can I take a few more minutes to tell you about my institute? What we do over here?
Hello,
Yes,
sir.
sir. We are participant are interested to see, sir.
What?
Sir, as a participant, I am very much interested to see your institution virtually, sir.
I didn't get you.
Yes,
Sir,
sir.
sir, we are interested to see your institution. As you are telling.
Institute. Okay. Okay. So basically, we are based in Mumbai. Tata Institute of Fundamental Research is a research institute which is involved in fundamental research of sciences and mathematics. And there are various activities and departments. So right from astronomy, chemistry, mathematics, condensed matter physics, high energy physics, we are into cutting edge research at in all the fields of sciences. If you want to visit a TIFR, basically a TIFR opens to general visit on National Science Day. So it was actually, we had a program just last Sunday. So that's the thing. But you basically keep an eye on our website, and all the public programs are normally posted over there. That's roughly the thing.
Okay, sir.
But if you want us to come to Orissa and speak to your students, that is of course possible. So you can write a mail to us at outreach@tifr.res.in. I will put it in the chat box.
Yes, sir. Sure, sir. Sure, sir.
So yeah, so this is our email address, and our team can visit places and interact with students directly. So there are of course limitations coming in due to this media. Whatever is, see, this will not, live is live. I mean, what is seen in person is in person, and what is seen over internet is different. So of course that difference is already there, that that you already know. So that's it. So if you write to us, we can come with a mutual convenience. We can visit your schools and interact with your students, and perhaps introduce them to the science which is related to the textbook, but not exactly what is there in the textbook, like the little experiments that we did today. So the idea of this is to get the student thinking rather than studying and solving what is there in the textbook. Try to look beyond the textbook, but which is essentially based on textbook. That's roughly the thing. So that's it.
Thank you, sir.
Sir,
I have gone through one or two books of TIFR, that is small science. Is it available for the public, for primary students?
I think those books are published by our center called as Homi Bhabha Center for Science Education. Is that correct?
Yes, sir.
Are you referring to those books?
Yes, sir. Yes, sir.
Yeah, of course, of course. Basically, I think some of those books are available in electronic format, or if you want a print copy, on the Homi Bhabha Center's website, there is a way by which you can place an order and get the books. That is possible, yes.
Thank you, sir. Thank you, sir.
So, anything
Sir,
else?
can you tell the name of the book?
Actually, there are several books. There are several books. To say, if I say one or two books, that will perhaps not be correct. So what I would suggest is you look at the website of Homi Bhabha Center for Science Education. That is, I'll write the
Sir, can you
URL in chat. I'll
type
write
the
the
name of the website in the chat?
yes, yes. Okay, so this hbcac.tifr.res.in is the name of, is basically the website address. You can look for the books over there, and if there is anything which you require, you can of course email us at outreach@tifr.res.in, and we can do our best to help you out. So, anything else, sir?
Sir, may I speak, sir, from Regional Science Center, Bhubaneswar?
Yes, sir.
Sir, is it possible for your outreach program to come on live programs on online programs for schools? Suppose they request you. So, is it possible?
We can try with a mutual convenience. Yes, we can definitely try. We can definitely try.
So, this is the advantage for the schools, because you know they will have a direct program for
Correct,
their
correct.
children organized by your
Correct.
platform.
Actually, we already have this. We have what is known as a Chai and Y session. I'll put you another URL.
Sir, can students also request the outreach program to come to their school?
Actually, at this stage, it will be good if you come via school. Okay, right now, what I have what I have put in is basically the website of our outreach. Okay, so right now what we have is every alternate Sunday we have a outreach program which is online, and everybody or anybody can attend. So it's via Zoom, and it's also available on YouTube. So if you look at this website, all our programs are posted there, and if you find it interesting, you are welcome to attend.
It's a beautiful idea, sir.
Actually, some of our previous sessions are also available on YouTube. The details are on this website.
So I request all participating teachers now to interact with sir for some time if they want. You please clarify your doubts immediately, because you know this is a chance, you know, we are getting to discuss with so many people from India at the same time.
Good afternoon. Actually, this for this grape experiment you showed.
Yes.
So that is that magnet is normally not available. So it's not a neodymium magnet. No?
Yes. These are basically very strong permanent magnets, rare earth magnets, NdFeB magnets, and they are commercially available. I mean, we are also.
Can you please write down that in the chat box?
Yeah, Brahmananda sir, you know, these things are already available in Amazon and Flipkart.
No, sir. This magnet is not available in Amazon, I'm sure.
Yes, sir, available. We have purchased so many times and it is available.
Actually, in that case, what you can do is, if you don't get magnet of enough strength, you can try stacking 2-3 magnets and check if you get higher field. But of course, it will be limited by various things, and it will not go up indefinitely.
Sir, it is available.
Yes.
It is commercially available. No problem, sir. You can get it.
Okay.
Actually, none of these experiments require any high-tech equipment. The whole idea is
this is most important.
Almost everyday object. That's the whole idea.
This is most important for all our teachers community.
Actually, yes. I mean, I think if the material is easily accessible, then it is demonstratable. Otherwise, it is not demonstratable.
Because our target is not to focus on a lab rather than our modified lab.
Yes. So these are basically what we call, these are actually wonderful lab called home. The whatever I presented today, they are from a set of experiments which we normally do, and they are titled Wonderful Lab Called Home.
Now, sir, would you actually listen from some teachers, who find science interesting by doing something in their own level in their schools? So I hope some teachers can come forward and share your experience on this platform, and we will be happy to listen that who is doing something at least in their school level apart from the lab activities. The response is not actually up to mark. What I find, that is a big problem. If you have to communicate properly so that all should be happy to interact with each other. It's not that one way listening. Somebody is
Sir, can I add something?
Yes, free to ask.
Sir, I'm not a teacher, I'm a student, and I can say that I really like this session, and I would really love for this team to come to our school and also give us more insights in science. So
Your
everyone
class,
can also
may we know your class level?
Class 8, sir, from Kids International School.
That's a good idea. So you are very happy to join this session, na?
Yes, sir. I really loved it, even though I didn't know most of the answers. But after knowing the answers, I'm like, oh, it's so easy.
So you go on doing experiments, inspired by our famous experts, right?
Yes, sir. So I'll play this in our class also. Like, please join these sessions and also like learn more about science. Not in only the textbook, but also in experiments.
Actually, science has only two prerequisites. One is curiosity, and second is careful observation.
Yes, sir.
All will follow. If you are curious, you will look for the answers, and the desire for answers will make you a careful observer. And that will take you to the questions that you find no answer to it, but you will find answer to it.
That's a good idea, sir.
So that basically the starting point is this curiosity, and then you should be willing to work relentlessly for it. If you have a question which is unusual, the answer will not be ready-made, and one should be prepared to work for a satisfactory solution relentlessly. It is always possible that what is one answer may not really be the scientifically correct answer. So that is why it is important to verify something via multiple routes to understand the underlying science for it. Okay, so you can perhaps, yeah.
Any other view? Our Adarsh Vidyalaya Sangathan, sir, sir, in Odisha, there has been a parallel management like a Kendra Vidyalaya Sangathan. Odisha government has initiated Odisha Adarsh Vidyalaya Sangathan.
Okay.
And fortunately, we could discover there are many rural children who are actually intelligent and did not get chance properly to show their skill, and at present through Odisha Adarsh Vidyalaya Sangathan systems.
Yes.
They are coming up, and their result is quite a big achievement.
Yeah, actually, our country, of course, we are a big country, and there is no dearth of talents. It's just that the talent doesn't get exposure at the right time. If we are able to introduce right things to the students at the right age, I think we can do wonders.
So this time in our program conducted by Regional Science Center, we have taken special care to invite teachers from Odisha Adarsh Vidyalaya Sangathan. And they are already included here also. Many of the participants are from Odisha Adarsh Vidyalaya, apart from teachers from DAV. And the famous KIT Campus International Schools. So there are a number of schools, but thing is that I do not know how many of us, really enjoy doing by ourselves. That is more important.
Yes. I think what you are saying, sir, is perhaps a nationwide thing. What is there in Orissa is the same difficulties across the country. And I think teachers will be able to find an answer to it. Teachers and students combined force will find an answer to it.
Yes, and hopefully your institution is a in a pioneer in the science education part as far as outreach programs are concerned. And the moment I listen that you are also coming to different places all over India on request, this is outstanding achievement.
Actually, sir, we can come. I mean, it's just all that we require is some bit of a local support and students who are willing to listen.
This is a milestone.
We can
I think this is a milestone for our Indian schools.
No, I think we are. There are a good number of science communicators in the country, and I think people are quite open to visiting the places.
Right. Thank you so much, sir. If possible, we will also be in contact with each other so that we can go ahead together for many other occasions.
Yes.
So it is a strength to our country, sir.
Thank you very much for for this opportunity. Thank you.
Thank you so much, sir. All your team members, your institution, and our participants for getting enriched out of this presentation.
And they can actually write email if something comes later to the mind. They can send an email.
Excellent.
We'll try to.
Everything has been made public, and it is only they have to show their interest.
Yes. Okay. Thank you very much. Thank you.
Okay.
May I leave now?
Yes, sir. Yes.
Okay. Thank you.
We close the program now.
Bye, sir.
Bye.